My name is Dr. Shobbusha Sen. I am the Dean Research and Development of JIS College of Engineering. But herein I am here to talk about my physics courses. Okay, I am basically a physics teacher. I do take physics in the classes in the BTech courses, so first and second year. So now here I am talking about my second year courses, which is called Physics 2 courses. Now, second year course in Physics 2 is separate for separate branches. For computer science and IT, bokeh is something. For mechanical, civil, it is different. For electrical, electronics, all are different. Obviously, they are learning in a different semester. Now, it is stream specific. It is as per the requirement of your own subject. Okay. Say in the computer science and IT syllabus, we have added the latest computation like quantum computation. Like the applications of latest materials called nanomaterials, how the storage and display devices works. These things are not so much connected with the mechanical and civil engineering, who are also learning physics 2 in this course. So we have kept courses like the ultrasonics, okay, which is applied in mechanical and civil. The concept of building acoustics for civil, which is not needed for you. So basically, we have made it stream specific. We made a thorough analysis of the requirement of your course from your department, from your alumni, from the existing student. We made a survey. Based on that, course objective and outcome was framed, and let me present the same now. Now the course objective of this Physics 2 course for CSE and IT student is to introduce topics, okay, is to apply quantum mechanics for learning the latest of computation called quantum computation, learn quantum logic gates. Is to, as a student, you get comprehend about the hardware sectors of your devices, okay, the storage, display part, and also the latest storage devices. The entire electronics is moving very fast, and that is because of the revolution in semiconductors and now the nano devices. Okay, so an introduction to that. So that will be another objective of this course. And also this entire communication system, okay, it's based on the electromagnetic theory. Okay, so we'll also provide you some glimpses of electromagnetic theory, because later on you have got courses on the analog communication and digital communication. Okay. Now the major course outcome of this Physics 2 course for CSE or IT student is that after undergoing this course, you will be able to explain the electromagnetic theory with your basic knowledge of electrostatics, magnetostatics and electromagnetic theory. You will be able to explain the most modern computing devices using the latest idea of quantum mechanics and quantum mechanics principle. You will be able to explain the operation of the most modern storage devices, how it evolved from the magnetic storage to semiconductor devices. You will be able to judge the requirement of the latest material for the purpose of computing, for the circuit design, and for the storage material, that is the ideas of nanomaterials. Okay, so let us, and this is closely connected with your own program, so you can get that in the course outcome, program outcome mapping also. On the screen you can see the various modules that are present in this course, and you can also see the module that you will be starting with. We'll start with one of the promising modules of the course, as well as you can also see the topic that we will begin with. And in this particular class, whatever we will be focusing on, the related prerequisite, what is the objective of the class, and if at the end of the class you're supposed to get something from me, that is the outcome of the session. So that session outcome also you can see on the screen.
Hello students, very good morning to all of you. I hope all of you, it's all going very nice for you. This is going to be, I believe, my 11th class in a row on a topic called Quantum Mechanics 2, which is a part of your physics course, and it has been so far a happy journey. We have learned ABCDs of quantum mechanics almost. Last video lecture I shared the main postulates of quantum mechanics. Now today we will talk about the applications of Schrödinger equation, and how you apply that equation, what is the meaning of that equation, particularly after you know operators now. Okay, what are the application of that, how do you interpret a physical result or physical information. So that is something I will be talking about today. So first, solution of quantum mechanics problem begins today. Application of Schrodinger equation begins today. Describing a physical situation in the language of quantum mechanics begins today. We'll be actually explaining a very interesting problem. Today I'll try to present the problem first. That is how electrons move in a metal. You know, how historically it has all changed. And the moment quantum mechanics comes into business, how it is changing the course of discussion. So that lesson you will learn, okay, after undergoing this particular class. So the objective is very clear. We will apply Schrodinger equation for solution of problem, and outcome is also very clear. After that, you will be able to explain, okay, using the wavy nature of matter, how the physical situation gets modified. Okay, same physical situation, how it gets tuned. And in this journey, these are some of the common issues or common points you should remember. This is obviously my 11th lecture today. This is myself, and this is the mantra. In a quantum mechanics class, we talk about wave nature of the matter. Matter can be metal-like collision, that you know. Wave can be wave-like superposition, that you know. Wave can be metal-like photonic nature, that you also know. We are talking about the fourth issue, superposition phenomena of matter, wavy nature of matter. And if a matter becomes a wave, then the matter not becomes a wave, rather matter cannot become a wave. Matter is a matter, wave is a wave. Matter will show the property of a wave. Okay, so electron is following this green line, okay, is important to us, showing the wave nature of the matter. That wave is a probability wave described by the function psi. With psi we can do the intermechanics. We can develop intermechanics using the method of operators. Okay. And actually entire study we have actually presented in 5 points now. First point is that wave function psi is therefore the basic variable of quantum mechanics. Anything you do in quantum mechanics that you have to do in terms of psi has got no meaning. It's just a mathematical function. Modulus of psi square gives some physical meaning that gives an idea about probable position of the object. Okay, the probability of finding the object at a given point are thought by long back by Max Born. Okay, Born's interpretation this is. And any physical motion to describe, you have to measure dynamical variables. For every variable there exists an operator in quantum mechanics. You can measure any dynamical variable if it satisfies eigenvalue equation. There is another, because we cannot do anything, we have to rely on prescriptions of mathematics. Eigenvalue equation is an idea of matrices. If an operator satisfies eigenvalue equation, you can measure those variable with the constant as a measured formula of measured value. Average value formula you can also see, that is true for many particle case. And last day I discussed with example that any arbitrary wave function is not acceptable. Any wave function will be acceptable if it satisfies and those conditions. If it is well behaved, if it is single valued, if it is finite, if it is analytic. Okay, analytic means first and second value will exist, then and only then it is acceptable. Because we'll be solving problems now, so you'll see how it is differing. Okay. How it is differing. Okay, those results will come up. Okay, these are variety of psis. Okay, variety of psis are there. You will see how it is changing. Okay. Now, obviously, if we will now solve actual problem, we'll do application of Schrodinger equation to describe a physical motion of a particle. Okay, now this is a Schrodinger equation. Okay, you can see. I just look at the equation here. H cat means Planck constant by 2 pi. 2 is a number. M is the electron mass or particle mass, whosoever is moving. Psi is a wave function, which is a function of space and time in this equation. You can see, but we have separated it also out. Okay, in space part and time part was separated out using the separation of variable. That is essential now, because when we're solving problem, you have to solve this differential equation. V stands for potential energy. It will be 0 if no force is acts on the body externally, and it will be non-zero if some force is there. That is, if electron is under Coulombic attraction in a nucleus of an atom, inside an atom, Coulombic attraction of the nucleus, then because of Coulomb force, there will be non-zero potential energy, which is more realistic case. And if electron is under no force, then it should have no potential energy. Then mathematically it will be easy to solve. But you know, less physical evening. Actual physical situation like electrons in an atom is like that, V will be non-zero. So you have to take up those matter, okay, and there is right hand I is root over -1. So what I did, the top is the time independent dependent Schrodinger equation. we have used separation of variable to write down in time independent form rather. Okay, where everything is depending on space, and E stands for something there. So now what shall I do now? In between now, after between the last time I introduced Schrodinger equation and its time dependent and independent form, and now if you compare, you will see some more discussion have been made, particularly these lines. Okay, the ideas of operators. For every dynamical variable, there exists operator. You can see the list of operator. Like x means x cap, and operator form is x. P means momentum means p cap, operator form means first space derivative minus h cap del x. Kinetic energy means p square by p cap square by 2m t cap, that is, if you put the p cap, it is minus h cap square by 2m t to dx. If you only think you have to know p properly, potential is a function of x. X does not change, it remains unchanged. T plus v gives you Hamiltonian, and any energy is h cap del t. Now, this, you know, all the operators now. So with the eyes of operator, now you can revisit the Schrodinger equation. If you revisit this equation of Schrodinger, so you will get something new. So let us understand through some detailed calculation. Let me do some calculation. After that, I will come back to this topic. Okay, just few seconds. You see here, these are the list of operators I've already written for you, and that is the equation of Schrodinger in time dependent form, because here psi depends on time and space both. So we use separation of variable. We have written psi as a product of two functions, that is phi 1 x and phi 2 t in my class, and ultimately it was separated into space part and time part. This is the time dependent part of the Schrodinger equation. Sorry, time independent part of the Schrodinger equation in one dimension. Where E was a constant because of that technique of separation of variable, and this is the time part of this Schrodinger equation. So we have separated out. We have told you this is the time independent Schrodinger equation. So I ask you to today put some focus, because it does not contain any time part. So this is the time independent Schrodinger equation. You see now, if we use the ideas of operator, this equation should have a different meaning. According to the ideas of operator, I can write down this equation in this way: minus h cut square by 2m d2 dx2 plus vx phi 1x equal to e phi 1x. We try to realize minus h cut square by 2m d2 dx2 is actually one of the operators enlisted here. This is nothing but the kinetic energy operator, and Vx is obviously the potential energy operator. So this is like this much. E is a constant. Now T plus V makes another operator, that is Hamiltonian. H cap phi 1x equal to E phi 1x. Now if you look at this, here E obviously stands for constant. So if you look at this equation, it's a very special equation. You see here an operator H acting on a function phi 1 gives you back the function multiplied with the constant, which is very similar to this equation which I told you initially. What is the name of this equation? This is called eigenvalue equation of that particular equation. So this equation is therefore eigenvalue equation of the operator of H cap. What is the meaning of H cap? H cap means total energy, kinetic plus potential energy. So that means Schrodinger equation is nothing but an energy eigenvalue equation. And this constant, this is energy eigenvalue equation, and this constant E is therefore the measured energy. So if we now just have a rewrite the equation again, you notice that the Schrodinger equation is therefore can be written like this way: H phi 1x equal to E phi 1x. This is nothing but an energy eigenvalue equation. where E is the energy eigenvalue, or the measured energy of the system, and phi 1 is the energy eigenfunction. This is the energy. So this high is basically energy eigenfunction, the space part of the Schrodinger equation, eigenfunction of the energy operator. So that means this E stands for, therefore this E implies energy of the system. So that means if I solve Schrodinger equation, this equation of Schrodinger, particularly space part, d2 phi 1 dx2 vx phi 1x e phi 1x, if you solve this equation of Schrodinger, because it's a differential equation, I'll get the wave function, we'll get it by solving this Schrodinger equation, but we'll also get the total energy of the system. We'll get the total energy of the system, and which is a constant quantity. So we are expecting two information each time we solve the Schrodinger equation. Energy, we'll get a function because I am solving the Schrodinger equation, and also the energy of the system. And finally, your psi is expected to be the product of this phi 1, and space part it already solved. It is like e to the power minus it by h square. This is the total psi, but from problem to problem, we will be more concerned in getting this phi 1. Each time I get phi 1, I will also get the energy of the system. We will see it very soon, don't worry. So let me just again now time has come, I should present to the actual problem of quantum mechanics. Okay, so let me present it for you. Just a second, let me get back to the PPT a bit. Let me get back to the PPT. This is one, so you can get it. So now I will be talking about the actual physical problem of quantum mechanics. Now, so now let me talk about the actual solving physical problem of quantum mechanics. This is the first application of Schrodinger equation. So put all your attention. Problem 1 begins here. Now to talk about the problem 1, we will be a bit historical. Okay. So let me talk about the origin of the problem. So we'll be in time machine. We'll again get back to the year 1897. You know, 1897 is a very important year of the physics, because it is a year when J.J. Thomson discovered our favorite electron. Okay, in physics lab we have got an experiment, E by M experiment, the electron charge by mass ratio calculation experiment. That is this Thomson's experiment. Thomson has done that experiment. So please try to do that experiment carefully. There also you will get an idea about electron, how it moves under a field, its measurement of charge by mass ratio. So ultimately, some idea about electron was developed. Okay, the fundamental idea about electron was developed in 1897. So, and by that time, electron was identified by a particle with some charge, some mass. So the concept of specific charge came into business. So that is something you measured in the physics laboratories. Okay. So now, so it was regarded electron is a charged particle. Electron, if it moves, will get a current. All these concepts were there. Now, a scientist whose name is Paul Drude, in 1900, he was doing an experiment on the resistivity of the material. He actually compared resistivity of two samples. Now, one of the sample was a polymer whose resistivity is very low, 10 to the power, very high, 10 to the power plus 8 ohm meter inverse, and he compared that with the metal. Okay, he did it mainly with silver. Okay, it was like 10 to the power minus 12 ohm meter inverse. So it shows that metals are very good, has got very low resistance, resistivity means resistance per unit volume, and polymers are very high, are highly resistive. So this stuck to the mind of Drude. That means what is happening to the metals, why they are so special. So that the inside the metal resistivity of metal is less. Resistivity less means ki electrons are happy to move, freely move, they are moving. So he tried to explain it, why metals are so much such a good conductor. Okay, so this came to his mind. So he has set up a theory. Okay, and you see the picture, that theory was originated from kinetic theory of gas. Why? Because 1900, look at the year 1900, there is no quantum mechanics, because Planck is in the year 1900, Planck is explaining black body radiation. So no quantum mechanical ideas was not established by that time. No Schrodinger equation, nothing in his hand. And at that part of physics, actually black body radiation experiment was also a part of thermodynamics experiment. It was a part of physics was dominated by thermodynamics people, thermal physics people. Okay, same Maxwell, who will be disturbing you with his electromagnetic theory in a different class, he has given certain theory to explain the motion of gas molecules in a container. And you know, by this time you studied kinetic theory of gas in first year in 12 standard classes, that if you keep the container at a temperature T, all the gas molecules will move randomly with energy 3/2 kT. Because of randomness, they make collision. In between two collisions, they move in a straight line path, mean free path. And time taken for collision is on an average called relaxation time. So all these wonderful ideas were there, okay, in kinetic theory of gas, and it was very prominent at that time. So what Drude did, he has taken up the idea that just like the gas molecules moves in a container arbitrarily, and what is the speciality? Gas molecule of gas molecule, they do not interact with each other. Okay, similarly, electrons also move arbitrarily without putting force on each other. Okay, electrostatic or some other force on each other. They are all moving randomly. So this is called electron gas model or free electron theory. You are thinking electron is like gas. What is the speciality of gas? Gas molecules do not interact. They are all moving randomly. There is no absolute indiscipline situation. So they are all moving randomly. So in a metal also he thought that all the electrons are left hand side picture. This is the situation. All the electrons are moving erratically, randomly, no discipline. And if everybody moves randomly, they will collide. Okay, you see the picture? They're all colliding with each other. So collision means mechanical interaction. So Drude thought just like gas molecule moves randomly, collide, all these things in between two collision moves in straight line. Relaxation time concept, mean free path concept is there, average path length in between two collision. So similar concepts will prevail here also, because he is utilizing the idea from kinetic theory of the gas. So with that idea, he tried to explain. So this is called free electron theory. Just to introduce the problem, let me tell you what is called a free electron. You see the animations going on there. It is a sodium atom. The last orbital is electron is a last Bohr orbit. There is only one electron, that is 3s1 electron. Electronic configuration 1:2:2:6 3s1. The 3s1 electron is the final, is called valence electron, or now we'll call free electron, because it has got the license to do everything freely. In chemical bonding, it will participate. In photoelectric effect, if you make incidence of light, this will go out. In thermonic effect, this will be coming out because of heating. So this is called valence electron. You see the picture. Okay. So that is the concept of free electron. So any metal, therefore, is a consists of the free electron. You see, so free electron is the last electron. You have got 10 more electrons in your pocket. So there is 11 nucleus is there. Look at the nucleus. 11 proton, 11 neutrons are there. 11 proton means 11 unit of plus charge in the nucleus, and neutrons are neutral. So that nucleus, it is thought that it is keeping so many particles, it is too heavy to move. So there is 11 unit of plus charge and 10 unit of minus charge. They will together make the core of the system. Okay, that nucleus, you can see the picture here. If I move it, okay, the core means the 11 unit of the nucleus and 11 unit of and 10 core electrons. So 11 plus and 10 core electron, 10 minus means together some sort of positive ion. A positive ion core is made up. So core means nucleus, which is positively charged, 11 unit of 11 protons, and that 10 core electrons. So 10 unit of negative charge. 11 positive, 10 negative means ultimately some positive charge. But the total mass of this 10 electron, 11 protons, and 11 neutron, and many other particles are there according to particle physics inside the nucleus. So that total mass is much larger compared to the mass of a single electron, the last valence electron. So it is thought that this valence electron is moving freely. This is a free electron, and the remaining part, that positive ion core made of the nucleus and the 10 core electron and other particles inside the nucleus, is too heavy to move. So any atomic system you can imagine as a core which does not move. This is a positive ion core and free electron. As you can see there, positive ion core and the free electron. I have presented two pictures. Okay. So if you see every atomic system is like that. This is the free electron, blue one, and the positive ion core. So electron is moving freely, randomly, erratically, and the core is not moving. So if you consider the solid which is made of infinite number of atoms, infinite number of atoms are making the solid. Okay. So infinite number of atoms, each atom produces one free electron and one ionic core, and all the electrons are free to move. They are, according to kinetic theory of gas, they will be moving randomly. So infinite electrons. So it is, so according to Drude, you make an infinite sea of electron. The waters of the sea is like electron, and in the sea you get some islands. The islands are the positive ions. You see, water moves inside the sea, islands do not move, and with the water will collide with the island. So same thing, electrons will move randomly and they will collide. So how the collision take place, I will show you now. And collision, mind, it is a mechanical interaction. We are not considering any other interaction apart from mechanical. It's a mistake, note it. Okay. So now let's replicate the situation. So this is the situation. Metal means this situation. Okay, this situation. They're all moving randomly. Okay, whatever I told you. And so this infinite sea of electrons, those blue one are the electrons, it's a sea of electrons. They're all moving randomly, just like kinetic theory of gas, colliding with the ions are the red balls. So in the sea is made of the blue electrons and red balls are the ions. Ions are like islands, they don't move. It's a process going on, just like gas molecule moves randomly colliding, so electrons also doing the same thing. Okay, now let us try to realize the whole situation. I hope you realize, okay? Realize the whole situation with a single electron. Okay, so this is the sodium ion system. Suppose the temperature of the system is say T, okay? T is the temperature. So any, just like the gas molecules in a container moves with the kinetic energy 3/2 kT, electrons are also moving 3/2 kT kinetic energy. I show you one electron. So suppose that electron is moving with the velocity v1. So it will collide with that sodium ion. So it is after collision, it has got the chance to move in any direction because motion is random. So there are so many options I have given. One of the options I have chosen. Suppose it is moving with velocity v2. Now it is colliding with that one of the sodium ions, that v2 as shown by the arrowhead, right hand side second electron. Then you can see after collision it can move in any direction because motion is random. So I choose one of them. Suppose it is moving with the velocity v3, and that is minus, you see v1, now it is now minus v1, and this last one is moving with the minus v2 velocity. So plus so ultimately what is happening, you see, because of that, you see, whatever with the velocity you are generating, ultimately you are generating no velocity, because the motion of the electron, if you look at all the motion here, the first this is moving along this plus v1, this is v2, so this is now minus v1, so plus v1 minus v1 just cancel, this is minus v2, so net velocity generated is 0, so no net motion. Okay, so why it is happening? Because of randomness, no discipline is there, all electrons are moving randomly. So if random motion means infinite electron, they can move in infinite possible ways. So if there is a electron moving with plus v1 velocity, there must be an electron moving in minus v1 velocity. If an electron moves with plus v2, there must be an electron moving with minus v2. So ultimately you generate no net velocity, which is 0. Okay. So no net velocity you are generating. So ultimately if electron does not flow, you do not expect a current. Okay. So what is the problem? Problem is discipline, less discipline, no discipline. So now to make a current to flow, you have to make the electron to move in a definite direction. So electron needs somebody whose instruction it will follow. So who is that somebody? That somebody is Mr. Electric Field. Because electric field will exert a force, electrostatic force Q into E on a charge Q. So that what electric field does, electric field E asks charge Q that Q, this is the force on you, follow me. So similarly, electron will experience a force. So that force will ask the electron to move in its own direction. You see what happens now. So now if we apply a force V1 now, you see all other directions are off now. So it has to move in a direction V2 only. Because if you apply the electric field in the, suppose that we apply the electric field in that arrow, so you see all other directions are, you see after collision, And now that minus v1 cannot generate, because after that collision it has to move in the direction with a velocity v3. After v3 it has to move with the velocity v4, because these are all opposite to the direction of electric field. Why? Because electronic charge is minus e, so force exerted on the electron by the electric field is minus e into electric field. If you apply force E on the charge Q is the applied force. So what it does, electric field asks electron to follow it. That is the job of a force, follow it. But electron is a bad boy. So bad electron, because it's a bad boy, it does not hear the voice of the electric field. It moves in a direction opposite to the field because of the minus sign. So if electric field is along left side, the electrons are moving in a direction opposite to the field. So ultimately at the end of the day, you notice there is a net flow of the electron. Okay, there is a net flow of the electron, and ultimately electron moves with some velocity. This velocity of electron, it will get some average velocity. Average velocity of electron under the external field is now, it's called drip velocity, and because of drip motion, this is a allowed direction. Okay, and ultimately you get some current we will be getting. And this is a theory that is used to obtain Ohm's law, that is V is equal to IR formula you studied. You have only knew the formula in school. Only school you have been introduced that volt, if this is happening, this is proportional to that. But that is not a theory, this is the theory. Theory is this one: electrons are moving, they are colliding, that is original resistance or resistivity. Connection between voltage and current is V is equal to IR. You can write down that in terms of current density as J is equal to sigma E. J is the current density, sigma is the conductivity, is the electric field. So that is also Ohm's law. So that law you can generate out, you can actually get it from this Drude's model. So it is a success story that getting Ohm's law is one of the success of the Drude's model. You can connect electrical and thermal conductivity together. That is also another success story of the Drude model. But main problem is that you cannot use this law beyond metals. It is good for getting Ohm's law. Ohm's law is still valid. So Drude's model is very good for that. But if you have to, but this is the age of semiconductors. This is the age of insulators, bad conductors. So if you have to explain semiconductors, then how do you explain? Because this is only true for metals. Then what it was done, Sommerfeld in 1928 actually has given a theory. Okay, that is also free electron theory, very similar to this model of this theory, that free electron theory that's provided by Drude. Electrons are moving, making collision. Only change is that he thought that utilized, because in 1928 quantum mechanics was there. He utilized the quantum ideas. Okay, this is the journey of the electron. Electron is, okay, that if you consider this is a mean free path, suppose an electron is moving from along that velocity direction v1. Okay, we'll focus only on this direction, but now we'll not consider electron as a matter. If you use quantum idea, the probability waves of electron you will consider. Okay, so if you do so, if you describe that much, so you consider only probability waves of electron. Okay, how it moves along that path as shown by that arrow. Suppose the position of the first atom A is at x equal to 0. Position of the atom B is at x equal to A. So journey of the electron will be from x equal to 0 to x equal to A. That is nothing but mean free path. So how it traverses through that mean free path length A, that is the point of discussion. If I could describe this problem, I can describe the other problem also. Okay. So this is my problem, how electron will be moving from here to there. To me, electron will be, I have to rely on probability wave of the electron. So that's described by function psi. Is the wave function, mod psi square is the probability of finding the particle. You can see the example, the electron is moving from 0 to A. So probability of finding the particle will be non-zero between 0 to A and 0 elsewhere. So at x greater than A, that is beyond the second sodium, x equal to A, it is 0. Left of x equal to 0, it is 0, and it is non-zero between 0 and A because electron is moving there. So I have expressed it in terms of size. So now you see I'm presenting the problem in terms of quantum mechanics. So why you see why it cannot go to x greater than A or x less than 0? Why it cannot go there to x greater than 0 or x less than 0? Because ions are there. So ions are creating two barriers, energy barrier in front of it. Two infinitely, because it cannot go, we think that it does not have enough energy. So as if both the barriers are infinitely high, so as if electron is trapped between two infinitely high walls, so that it is restricted to between two ions. And in between two ions, it is mean free path. Mean free path means no force acts on the body, so potential energy is 0. So it's a journey of an electron, therefore from x equal to 0 to x equal to A, and it is restricted to between, it is at x equal to 0 there is an infinite wall, that is an ion. at x equal to a, that is another ion, okay, and the particle electron is restricted, confined to move between 0 and a. Between 0 and a, it is mean free path, so no force acts on the body, so it's happy journey, potential energy is 0. So now we have to, we know, you can see their wave function is non-zero only between 0 and a. Okay, so your job is to find out this wave function using the ideas of quantum mechanics. Okay, so who will give me psi? Schrodinger will give me psi. So we'll solve Schrodinger equation now. Now, just wait a bit. I have presented a long problem. So first realize the problem. Okay, after that, first comprehension is best. Okay, so this is my problem. I have tried to explain it as electron flowing in a metal, but in general, this is called one-dimensional infinite potential wave problem in quantum mechanics. It is applied in many ways. In nanoelectronics also, nanomaterials, we'll be talking, there also it is applied. So try to realize this problem very carefully. It's a very important problem. First problem of quantum mechanics. It is not difficult problem. The solution of the Schrodinger equation is very easy. It is almost done. Okay, you can do yourself also. But I will do it for you in the next video lecture. Okay, thank you.